There are 8 million YouTube talks online, but if you want to really experience it, you have to come in person. It's great. I mean, you'll just meet such cool people.
Welcome everybody, thanks for coming. I know there are a lot of super interesting talks right now, so I'm grateful you're here. In this presentation, I'm going to discuss mostly two topics. What is behavior trees? So if you don't know anything about it, that's okay. And then more in detail, I'm here at CppCon, so finally can, in one of my presentations, discuss the details of how BehaviorTree.CPP is implemented. BehaviorTree.CPP is a library that I have been maintaining in the last 5 years. A little bit more about myself. Davide Faconti, nice to meet you. Robotics is my life. I've been doing robotics my entire career. I started at the beginning with the humanoid robots. That is a lot of fun. Locomotion algorithm, hardware design, 3D physics simulation, and a lot more. I worked with the AGV and wheeled robots, mostly in the area of navigation, localization, 3D perception. Also, I work at Picnic, and I know about control of robotic arms, real-time control. Then I love a lot tooling and logging. That, if you ask me, that's a weird thing, but I really like that as a topic. And then I really like CPP. I know that nowadays people don't say that. You're not supposed to say that anymore. But I do, and I learned a lot watching videos on YouTube from CppCon. So you can imagine how excited I am to be here for the first time and presenting. So, because I was so excited, I started watching videos about how to give a good presentation. And all of these videos say you need to connect with your audience. And I have the perfect way to connect with you. So today is my birthday. So so it is literally my birthday. So I think it would be wonderful if the audience of CppCon tell me happy birthday all at once. So I'm going to count up to 3, and you're going to say happy birthday. Are you with me? Yeah? Okay, 1, don't let me down, okay? 2, I'm counting on you, okay? 1, 2, 3. Happy birthday! Thanks, I didn't expect that. Okay, so now we are like family, right? I can say whatever I want, but we are connected. Good. Okay, now the real presentation. So how did I end up developing this library? Well, the motivation, and of course, okay, here it is. So this is an old project from 2017, I think. It's a mobile manipulator. This was a project, a pilot project in collaboration with a car manufacturer, Seat. And in this video, you can see this mobile robot with a robotic arm, using computer vision and a 3D camera to find objects and move them from one place to another. I think this video is also a good representation of why mobile robotics is not successful commercially. So, because this is very slow. But the project was interesting, and here there is a typical application we have in robotics. Many different components, one for autonomous navigation, another one for the arm, the gripper, the camera, and all these components need to work together. And you need to define the behavior, the task that the robot needs to do. In this case, is a simple pick and place, with some logic about the number of elements in the tray. But as a developer, I needed to implement this logic, this business logic. And of course, the normal thing to do would be to use a state machine. But what I did was to explore, at that time, more options. And next slide. Sorry about that. So, and I find out about behavior trees as an alternative to state machines. And they were particularly popular, and they're still particularly popular in the gaming industry. I believe they started being known in that community in 2005 with the Halo 2, that used them for the first time. And nowadays you can find them, for example, in the Unreal Engine. And they're a good example how you detach this particular problem that is designing the, let's say, kind of intelligence behavior or intelligent behavior of your agent from the hardcore C++ implementation behind that. So I started using behavior trees in the project, and to give you more an idea of where the behavior tree fit into a robotics system, you need to understand that nowadays, well, actually in the last 2 decades, robotics has been mostly dominated by the concept of component-based software engineering. And that's funny, because 99 roboticists don't even know what that is. And people that know what component-based software engineering is say that roboticists don't do that well because they don't formalize the meta model or meta-meta model of their system, so boo. But the truth is that we're really doing that. So we use multi-process or multi-nodes, nodes in terms of computing nodes, distributed systems. We have inter-process communication with a publish-subscribe or request-reply pattern. And theoretically, we want each of these nodes of the system to have a single functionality. We want to do something in particular. As I said before, control the arm, control the gripper, or the mobile base. But once we distribute these skills in multiple nodes, we need a centralized element that coordinates them, that orchestrates all these functionalities to achieve a certain task. So we usually call this, as I said, coordinator or task planner, and is where we have the highest level of abstraction in our system. So where we focus on what the robot should do and not on how that is done. So we don't focus on the particular algorithm or particular implementation. We have a very high level of abstraction that say, do that, go to that certain location, move to that certain pose. And so this is where behavior trees fit as a potential way to implement this element of the system. And you can do it in other ways, where you can use state machines, you can just write, nested if then else, or switch statements. But behavior trees is a popular way to solve this particular problem. And nowadays, BehaviorTree.CPP is used in many, many projects. So it's really growing in terms of adoption. I know it is used in legged robot like that one. I know it's used in drones. Recently, I found out that underwater robotics is also using BehaviorTree. And of course, in the context of robot manipulators like that one in industrial, it is very popular. And this, even if I know that you need to take this with a grain of salt, this is the number of GitHub stars over time. And I know that doesn't really mean much, but gives you an idea of the adoption. And also this is something that I listen when I go to conferences and people tell me, hey, I'm using that library. So I can really say that it's becoming slowly the de facto standard in this domain. So, but as I promised, you don't need to know about behavior trees, because I'm going to give you a very short introduction now. So, there on top, we see a more classical state machine. Here we want to open the fridge, grab a beer, and close the fridge. And we can have 2 transitions from each of these blocks. And you can see that, each of these blocks needs to succeed so that the entire grab beer from fridge is done. And if each of these steps fails, then this routine failed too. We can express the same with the behavior tree below. Don't worry, I'm going into the details, but I want you to see immediately how the graphical representation is different. And that is important because we do have tools for graphic visualization of behavior trees. And something else I want you to notice is that the location of the boxes in the graphical representation has a meaning. So if I move those blocks in the state machine around, nothing changed. So it's just a cosmetic thing. But instead, when I look at the children of a certain node, like in this case, the sequence node, they're ordered from left to right. This is a big advantage in terms of readability, because when you look at a graphical representation of a behavior tree, you can scan with your eyes from top to bottom and from left to right. So it is much easier to read a larger behavior tree than a big state machine when you start very soon to have spaghetti of line crossing each other. So when people ask me when should I use one or the other, or what is the advantage of behavior trees, I think that this is the most scientific way I can describe it. So we all know that complexity in software is bad. We all know that there is a limit where my ability as a human to understand the code becomes limited. So the computer can understand a very complex code. It is the human that cannot understand it anymore. So based on the size of your behavior, there is a limit where you don't understand it anymore, or other people don't understand it. And it's always exponential. There's nothing we can do about that. But we can change the rate at which these grow. So in my opinion, hierarchical state machine reached that level of not being understandable anymore pretty soon. Behavior trees in general reached that limit much later. And then what I've been trying to do, in particular in the last couple of years with the new versions, is to move that limit further and to give more expressiveness to the library so that we push that complexity limit to bigger sizes. And this is as fair as possible comparison between the advantage and disadvantage of the two approaches. So first of all, let's be clear. State machines are more familiar to all of us. If I ask you to take a napkin and a pen and create a representation of the behavior of your robot, you will probably create something that resembles a state machine. So behavior trees need some, let's say, they have a learning curve. Then concurrency. Behavior tree do model concurrency. I will go into the details later. And that is really hard to do with the machine. I've seen recently some efforts to do that, but historically that's not possible. Scalability, as I said, is poor compared with the behavior trees, and the readability, for the reason I explained, is also better for behavior trees. So let's understand how this works. So sorry for the. So this animation, I couldn't put it in a loop. So I'll show it to you again. The idea is that you have, just to visualize it, imagine this concept of a tick as a signal that goes from the root of the tree until it reaches the bottom on a leaf. So the leaf is where something happens, where actually we execute some code written by the user. So only when this tick reaches the bottom of the tree, it is when something happens. In this case, open the door, walk, close the door. And the role of all the nodes in the middle, in this case, the sequence, is just to direct this signal to the right child. So each of these boxes can only return to its parent success, failure, or running. That's the only kind of values it can return. And based on these return values, as I said, the control nodes in the middle, that's their name, will decide where to where to dispatch the next tick. Then there are exceptions, so conditions are like actions, so they are leaves, but they are assumed to be atomic, synchronous, and have no side effects. Of course, I cannot, since this is just a convention and there is where you put your code, I cannot guarantee that your code fulfill those expectations. And then decorators are a special kind of control nodes that only have a single child. So once again, just to see this animation. So you see how we're scanning from left to right, and then once we have completed, the sequence itself return its value to the parent. So how a sequence work? The logic is simple. Take one child. If that returns success, move to the next one. And if all of them are successful, then the entire sequence is successful. But if at least one of them fails, interrupt the sequence, and the entire sequence fails. So in this case, for example, if a door is closed, then the entire sequence stops and return failure. The other building block that is used is the fallback. It is kind of the reversed logic. The fallback is more like try to do this, if you can't, do the other one, and then do the other one. So in this case, you will check if door is open. If it's not, then you try to open the door. And if you fail to open the door, then you smash the door. If any of these three children return successful, the entire fallback will stop and just return success. So you can see that these are the two main building blocks that people use to build basically every kind of logic. Then we have decorators. Decorators are something that enrich incredibly the expressiveness of our tree. In this case, I'm showing two of them. One is an inverter, very simple. Whatever my child return, I will return the opposite. And in this case, for example, an inverter plus is door closed is equivalent to is door open. And then I have this other decorator we try with a maximum number of attempts of 5. So I said, okay, if you can't smash the door, you can try again up to 5 times. And if at the 5th time you can't, then this fails and the entire fallback fails and your sequence fails. So you never enter the room. So you can see that doing the same in a state machine would be very complicated. So you can see how this very simple mechanism really help you express more. There's a question there.
Yes, when you say retry attempts to 5, does that mean that when the tick gets to that retry box, it's going to try smash door 5 times in a row, or it's going to wait 5 ticks and then after that it's not?
That's a great question. That is an implementation details and depends from how that is implemented. And since people expect sometimes one behavior or the other, I have 2 versions of this note. Because that's a complicated topic, but very, very on point. Usually, you should not make any expectation about the number of ticks required. You should just have a while loop until reach some end state. You should not say, oh, I believe this will need 10 ticks or 20 or 100. Other examples are force failure, so whatever the children return, I'll fail or success. Repeat, that it will stop if, repeat 5 times, but if any of these fails, then you don't continue. Timeout, run once. Anyway, the idea is that you can use this very simple piece of logic to express more complex behaviors. So let's have an example. I want to implement a very simple if-then-else logic, right? How can I do that? So I have a fallback. Let's see what happens. So if is enemy, if it's true, then that's a sequence. I go to shoot that enemy, and then fallback will stop, and I successfully kill my enemy. And if his enemy is false, then sequence is interrupted. The fallback will go to the greet branch, and I will say, hey, hello, you're not an enemy. So we can see the bug. There's a bug here. Of course, you're not familiar, but what happens if I miss, when I shoot my enemy, I miss it? So what happened with this tree is that if shoot fails, then I go into greeting the enemy. So I say, shoot, no, sorry, I changed my mind. Hey, how are you doing? Right, so there is a bug in this version of if then else. So the correct way to implement it would be this one, where we have a branch for when his enemy returns success, another one when he's not an enemy, so because I have an inverter there. So this does exactly what I expect from an if then else. So who likes this? no, I don't like this. This is stupid. I mean, the if then else is one of the most basic blocks in in programming. So this demonstrates composability of different logics with different building blocks. But you want this, right? If then else. So if the first child return success, I will execute the second child, otherwise the third one. And it's incredible how this is not mentioned, that this particular control node is not mentioned in any literature about the topic. So, but what I want you to see here, so I created this one. It's not in the literature. So, is that you can think about behavior trees as an extensible domain-specific language. You want to express something that the building blocks you have can't express well? Create your own, no problem. So of course you are supposed to implement the is enemy, shoot, and greet. But you can also implement your own decorator, your own control node, and then have a specific logic that I don't have in the library because I can't think about all the possible cases, and then would be very bloated. But here there's a trick. When I start thinking about this as a domain-specific language, then I realize, something changed in the way I look at the problem. For example, if I think about programming, what I usually do is to use function or routines to express a higher level of abstraction. For example, I may have the function fetch the beer, and inside I have something like a sequence. I go to open fridge, grasp the beer, close fridge. You can notice something. I have arguments. So a node needs arguments, needs inputs, and also it needs to return return values that are used as input by others. So we need a data flow mechanism between nodes. And I need to encapsulate this kind of logic into this fetch beer function and reuse it. So this means that I need a way to express subtrees and reuse those subtrees without copy and pasting. Perfect. So this was the introduction, and let's talk more in detail about the library itself. So if you remember the story about my project and the mobile manipulator, you will know that, okay, now I'm sold, I want to try this behavior tree thing, and I found a Python library that would do. But if you guys and gals find a Python library that does what you need, what would you do? Of course, do it in C++, right? I would never use the Python library. No, so in fact, there was also a tiny C++ version that I decided to fork and maintain, and that's basically what I've been doing the last 5 years. So I started from an existing small library. So this is my face when I saw the Python version, right? I said, no, come on. And but also there's a more practical reason is that in robotics, most of the people and most of our software use C++. So I really don't want to spend time doing binding to Python. I could, but what if I have a framework that make C++ usage easier for me? So these are the main features of the library. First of all, I want C++, but I also want the flexibility of a scripting language. So, and I'll tell you more about this later. So I want to be able to change, my trees without recompiling the entire application. Then we consider as first-class citizens the asynchronous action, so action that require a certain amount of time to be executed, and reactive behaviors. So reactive behaviors means that if something happens, you can react in, let's say, as fast as possible and maybe interrupt something you are doing. So this asynchronous action should be interruptible. Then there's a lot of tooling. If I have time left, and I guess I will, I'll show you all the tooling that was developed. So the graphic interface to debug behavior trees. And there are a lot of tools also for debugging. So debugging is very important in this case because we are talking about, as I said before, when you talk about behavior trees, What you're really talking about is the behavior of the robot. So we want to debug that and see if my robot is doing something unexpected, the why that happened. So I have a lot of tools in the library to make that easier. And then finally, some novel concept that I haven't found in the literature. This is really something novel, my small contribution, having pre and post condition on top of behavior trees as an extension of behavior trees. The main principle I'm following when I think about how to write and evolve the library is, first of all, productivity. So I always focus on trying to make my user more productive. So having a more expressive API or being able to do more with less nodes. Because as I said, as the tree grows, so does the complexity. Composability, this is a fancy word to say that ideally, in an ideal world, I want to decouple the person that created behavior from the person that write a particular action. So these people usually are in the same team or are the same person. But ideally, I want somebody to create a library of actions and then somebody else use them without looking at the source code and without modifying the source code and just reassemble them in a tree in the way that is more convenient, the most convenient for them. And this also brings to the concept of reusability, so having very general purpose nodes and not application specific. So to give you an idea of where the C++ and the scripting language is, imagine that your nodes in the tree are like pieces of Lego, and those are in C++. But the way you assemble them in your tree is done with an XML. And XML maybe is not the greatest format, but I can tell you that the alternatives were worse. And it's very good to represent trees. So that is the way I basically put together these nodes into a tree with an XML. Okay, so I'm very excited here because I never have time to show any C++ in my presentation, so this is the first time I can. So this is the way you build a C++ node. So first of all, you inherit from a class, in this case, a synchronous action node. So there is the assumption that you will return a success or failure immediately when you are ticked. So there is this particular constructor that I will describe later in more details. This is the callback that the virtual method you need to override with your own implementation. In this case, the important part is that you return success. You do something and you return success. In this case, it's just printing some message. But you can also do, if you don't like inheritance, you can also do a more dependency injection style, I think. So you can, this is good mostly for legacy code you don't want to change. So as long as you can wrap it in a STD function, I'll show you how to do that, you can do that. But being honest with you, the object-oriented approach will give you, eventually will create less boilerplate, not more, because it includes a lot of functionalities that otherwise will require even more line of code to achieve. So of course, as you can imagine, if I'm creating at runtime a tree from an XML, what I need is a factory. Everybody here knows that that's the classical example of a factory pattern. So, So I do have a behavior tree factory. I have to register my nodes only once. So I'm registering, for example, here, an approach enemy node. And I'm giving it a name. That is the name that I will find in the XML. And there you can see how I can use a lambda to register also this function that doesn't use inheritance. How I wrap this legacy code into a lambda so that it is accepted as a node. Honestly, but mostly nobody does that, but I try to give the two options. And this is an example of the XML. So here I have a sequence where I approach the enemy and I shoot the enemy 3 times. So the shoot is wrapped in a repeat 3 times. And so what I do is create an instance of a tree from an XML. And then I have this tree that I can tick. In this case, I delegated the while loop to the API itself. So I say, keep on ticking until as long as the return status is running, and this will stop when either I succeed or fail. So here, in this example, you can see where the C++ and the XML stand in the system. Okay, I mentioned earlier that we need some data flow mechanism. So a very simple example. Imagine that I have a detect object and a grasp object sequence, right? So the output, the detect object will have as an output a certain pose. And the grasp object needs that pose to determine where the gripper of the robot goes. So I need some kind of data flow between these 2 nodes. And this can be done with any mechanism you have, but you want to express this in a way that is visible in the model. You don't want to do it implicitly in your code. I don't want to read your code to know that there is this data flow between these. I want to expose this. So the mechanism that is used historically in behavior trees is called Blackboard, and is basically a global key value map. About the global, we will talk about the global later, but for the time being, imagine that here, for example, I have this, the first block says something, accept a static string. So that's not a variable. It will always give as a message, hello. Then the second block is think what to say. So it will generate as an output something that will go into the key called the answer. So I'm going to write into the key called the answer, the string, the answer is 42. And then that will be an input for say something. So you see how I use these curly braces to make a distinction between a static string or the name of a key. So you say, okay, this is the address in the Blackboard where you can find the actual value. And this mechanism is strongly typed. So I'll show you some slide about how I implement that. But the idea is that this is strongly typed, so you can only connect ports with the same type. So usually you find when you read about behavior trees, they talk about Blackboard. What I expose to the user is a more expressive, I think, input-output concept. So there is a clear expectation about the fact that a node will interact with an entry of the Blackboard as an input or an output. So let's have a look at an example how this is implemented from the user's perspective. The way you declare your ports is through this static method. And it's a static method because this is not a property of the instance, it's a property of the class. So, and I don't want to instantiate the multiply to access the provided port. So it needs to be static. And then I implement my tick. In the tick, you can see how I get my input. And of course, what this return is expected. So that is so hot right now. So everybody say that you should use expected to return something that may have a code error instead. So this you can check if the value is okay. Then you use this value. And what I do is just multiply it by 2 and set it as an output. And if something was, if it failed for any reason, I print the reason why the get input failed. And usually it fails because maybe you have a wrong type or that variable was empty. Nobody put any value there. And the fact that this is static, I think, is quite interesting because there is some some steps that I need to do in at compilation time. So when I register the node, so if you probably you don't remember, but this is the function with the method we saw earlier, register node type. So when I register the node type, I statically, at compile time, I check if the signature of the constructor has this as a string and a node config, and if the static method exists or not. So the implementation of this has static method provided ports is left to the reader. You can look at that on Stack Overflow. So I immediately return, at compilation time, I warn the user if they forgot to add the provided ports, or if it's not static, or if there is typo, whatever. And then this is thanks C++17 for if context. Based on the fact that I do have that method or not, I execute two different ways to register the node. So this is the interesting part in my opinion. So about Blackboard, as I said, the Blackboard is conceptually very simple. Is under the hood is an ordered map with a string as key with a name and an entry wrapped in a shared pointer. There's a reason why it's a smart pointer and why it's shared. But let's have a look at what the entry struct has. He has the value stored in a any. So this is not exactly std any. It is another version I'm using that has 16-byte small value optimization, but it's basically like an std any. So this is the mechanism of type erasure I'm using. Then I have some type info, so I need to remember what the original type was, so I'm using this type index, and I think this is interesting. For each type defined by the user, potentially the user can provide a way to convert a string to that type. So of course I have this implemented for all the basic types, like integer, float, whatever. But if you have a point 3D with the X, Y, Z attributes, you can create a string to type converter and register that. And if you do that, it's convenient because then in your own XML you can initialize variables. So this is where I store as a function, std function, I store basically the converter, the string to type converter. And then I have, here a mutex because potentially this Blackboard can be accessed from multiple threads. So each of the entry individually needs its own mutex. So the mutex was the first reason why I needed, I couldn't, I was obliged to wrap this into a smart pointer. But it could have been a unique pointer. The reason why shared will be explored when I discussed subtrees. That is now. So about the hierarchical composability and subtrees. So as I said before, what we really want to have a language is to have function that I can reuse so that I don't copy and paste the same routines multiple times. And this is done with the concept of subtrees. So a node of my main tree can actually be an entire tree defined somewhere else. And the way I do this is at the level of the XML itself. So this big tree is created at deployment time when I parse the XML. And you can see how here in the main tree, I call the node subtree with a certain ID. And that will point me to that other beaver tree defined there. So this is the way I basically implement this composition of two trees, one including the other. Something important to mention is that each of these is an instance, not a reference. So if you have multiple open door, each of them will have its own instances. They're not pointing to the same subtree. And here is where I'm talking about the blackboard scoping. Each of the subtrees has its own blackboard. So when I said before, the blackboard is a global key value storage, not really, because we know that global variables are bad. We know that we need to reduce the scope of our variables. So what I introduced is the concept of that each subtree is isolated with respect to the parent that is calling it. So for example, here, open door will have its own blackboard, and main tree cannot see that. You cannot see that unless you need to, because if you want that to return a variable or accept an input, you need to pass something from the parent blackboard to the child one. And here is where we use port remapping. So stay with me, look at this code. Here we have the main tree where we compute the goal, we store it in a move goal. I'm using color to represent, so the blue one are the one visible in main tree, and the magenta are the one visible in move robot. So I update move goal, I pass move goal as an input to move robot, I expect it to return to me a move result, and I use that move result later and report error. So, and then in isolation inside the move robot, when I implement move robot, I have no idea what they expect when they call me. I don't know what the parameters will be, what the output will be. I just know that at my local level, I'm using target and results as the entries of my local blackboard. So it's the user that need to decide, okay, that's the way I map the target to move goal and result to move result, and that's the way you do it in the XML. There are some tricks to make your life easier, like flags. They say if they have the same name, how to remap them. So there are some tricks to remove the boilerplate, and we are discussing even more methods to do that. So it is a little bit verbose, but it's the only way you can really have this isolation in terms of scope. So now you get an idea of the main functionalities, but there is much more I'd like to discuss, and I have 70 minutes. So debuggability and observability. As I said, it's really important to be able to debug behavior trees. This is the logic of your robot, and you want to see when there are bugs, what's happened. So I implemented an observer pattern. I'm not going into the details, but I can tell you that this observer pattern allows you to subscribe to all the changes in the tree and do something when these changes happen. For example, you can save them print them on console, save them on a file or an SQLite database. You can publish them over the wire and display those state changes in a GUI. That's actually what we do. Or you can collect statistics, or you can even create non-intrusive unit tests. So without changing your code, you can record all the transition and checking if your unit test, the sequence of transition is the one you expected in a non-intrusive way. Then, that's funny. When I prepared this slide, I looked on Google for code injection, and apparently that's a thing. I didn't know that. Google is quite kind of interesting. It's a thing. So code injection and interactive debugging. This is a mechanism that I use to basically insert pieces of code before and after the tick. And that is a very powerful mechanism that allows me to do something like breakpoints. So I can insert at runtime breakpoints to a certain node, so the tree will stop where I want it to stop. Or I can do fault injection. I can say, hey, the next time you're ticked, whatever whatever is your result, I want you to fail because I want to see what happened to this other branch, the recovery behavior branch, when you fail. Or I can just substitute and say, oh, this is a camera node, but this robot in this moment doesn't have a camera. I want to substitute it with something, with a dummy one that I always return success. So it's a very powerful mechanism for interactive debugging. Then, script language on top of behavior trees. This was an innovation in version 4, and here I should say thanks to Jonathan, that is not in this room, but is at this conference. So I used this library from him. And basically what I did was create a scripting language on top of behavior trees. This scripting language is very simple. It allows me to do arithmetic operation, logic and comparison, A equal to or more than B, support enums, and basically the way it works is that the variable of the language are the entries in the blackboard. Let me show you. So this is the script node is where I run my, basically this scripting language. So here I'm assigning the string hello to message. Then I do message plus equal word. There below in the variable A, I assign 42. In the B, so one will be an integer, the other will be a double. So plus A, so actually the actual value is 45.14, and then color is under the hood is an enum, and you can see how I can have when A is greater than B and the color is different than blue, then you execute the sequence below. So this removes a lot of complexity from the behavior tree, because sometimes you can express something with a one-liner, and the alternative would be to create an entire node just to do that. So I had people before creating nodes that basically did a comparison operation. But where I really use that scripting language is as an enabling feature for pre and post conditions. So precondition are basically I have 4: skip if, success if, and failure if. So they expect something that returns a Boolean, so the return of a comparison operator usually, and they will skip the execution of the node if that is true, or short circuit and return immediately success or failure. And then there is the reactive version that is while. So as soon as they become false, they interrupt. And then I have post conditions that are executed later. So they're executed only when you succeed, only when you fail, or when you are interrupted. This is an example how powerful that is. So if I want to return, let's suppose that I have a move base that doesn't return any error code. So I want to implement the ability to save if that was successful or not in a variable that I can use later. The old-fashioned way would be this one with a sequence and then a fallback that forced the failure because I cannot succeed if mode base failed. So you can see how complicated that is. And now it is much simpler. I can just have 2 post conditions that set the variable. And actually, in the original version, I should use the numerical value of the enum, and now I can directly use the enum. Last but not least, the asynchronous behaviors in behavior trees. So as I said, in robotics, it's really, really important to have reactive behaviors. So imagine that you have a mobile base that need to go to the other side of a huge warehouse. And at some point, your battery level is low. You want to be able to stop that action and go back to your charging station. So you cannot treat any action as atomic. You need to be able to interrupt it. The way to do that is returning running. So when you return running, you are telling to the execution flow, look, I don't have, I'm still doing. I don't have an answer, come back later. Tick me later, I'll tell you if I succeeded or failed. And you should do this for any long-running action. Also, these allow you to execute multiple actions at the same time. The reason for that is that I'm using a concurrency model. Note that this is not parallelism. So this audience knows exactly the difference between these two concepts and don't need to repeat them. But in terms of expectation, you must think that the behavior tree itself is concurrent. So I'm going to, when I tick you, everything is done in a single thread. So if your method blocks me, there's no way I can move to the next method. So always, for the next slides I'm going to show you, always think about concurrency, not parallelism. And this is the example about a reactive behavior. So I have a sequence that is a compute goal, check the battery level once, and then move to that particular goal. So we check the battery level before we go to a certain location, but then we don't check it anymore. What will happen is that if move robot is asynchronous, I will tick it many times until it returns success or failure. But I will never tick again compute goal or check battery. If I want instead to check battery every time at every tick, I need to use a reactive sequence. So reactive sequence has a different semantic, and every time check battery level will be ticked before I tick again move robot. So, and if that return failure, then I will send an halt signal to move robot. That is basically calling a callback. This, for example, allows me also to do something like this. Use a parallel node where I have a robotic arm and I'm executing a certain motion, and I'm using the time, that could be a couple of seconds, to start computing the next motion. So these two things need to happen at the same time. So remember, from my point of view, I assume this is concurrency. So I'm going to, in an alternate way, tick first the first child and then the second child. But under the hood, of course, you need your own thread, because the computation you do in compute next motion or the control loop you do in execute motion need their own thread. And this in robotics very often is delegated to another process. So we use inter-process communication to delegate this to another location, or you need to create your own thread locally. So, but I don't deal with that. So this is an important message. I don't care about your multi-threading. There's nothing I can do to help you magically doing multi-threading. And I really want to, but I can't. I can't because, and I'll show you some example of why I can't. Because these actions need to be interrupted. And if I can, and I don't know how you will implement that. Maybe that it cannot be interrupted. And originally I had a node that would create a thread for you to remove some boilerplate, but then now it's deprecated because people expect that to work magically because I provided it, so they expect it always works because I did it. But there's no way I can control that. So let me show you, and here there is the last bullet point. I think it's important. There is the problem of starvation, but actually I think you can see it better here. So let's see this simple example. I have an action that takes a lot of time. I'm simulating that with this long operation. Imagine it's a sleep, 10 seconds, long operation, and it's blocking from the point of view of the thread calling tick. So the problem is that is the starvation of the tree. So I'm not returning the flow of execution. So there's no way I can check any other node. There's no way I can stop you. And then there is the halt method, but nobody's going to call it. And even if they do, that would have zero effect. So I need, to return the flows of execution as fast as I can. I cannot block. So a solution would be to use, would be this one. So here I'm using something different. It's a different base class I provide that is stateful action node. It's very simple. Instead of a single tick, I split that in two, in one that is called onStart and the other is called onRunning. So the very first time you are ticked, that would be an onStart. And in this case, what I do is launching a new thread with the std async, and that executes this long operation, and I return immediately running. So the latency I introduce here is as big as creating, calling this async. And then the next time on running will be called. As long as I'm in the running state, this will be the callback. And here what I do is in a non-blocking way, so with a 0 millisecond wait for, check if the future is ready. And if it's not, I return immediately running, so almost no delay. Otherwise, the long operation is finished and I return success. Problem again. How do I interrupt this? So now potentially I'm not consuming, the main thread is not starving, and somebody may send me an halt request to interrupt this, but there's no way I can interrupt that async in this implementation. So the solution, of course, is more complicated. You need to split this in small, in a while loop that can be interrupted. So it's up to you as a developer to implement this well. But I'm showing you, to make you understand that first, it's not an easy problem for me to automate for you. And secondly, creating asynchronous behavior is important if you want reactive behaviors, but it's complicated. I finished, 4 minutes left. Final remarks. I saw this a few days ago, this tweet. Let me read it for you. Look, I understand how to use Blueprint. I think this is Unreal Engine or Unity. I think it is Unity. And and all, but is this better than a couple of lines of C++ code? So I know that some of you are thinking this. Say, okay, really, can't you just write this? So of course I can write these behaviors as a bunch of if then else switch, and I can do that. But you must not forget that here we have different users in mind, right? The same person that write the action potentially is the person that write the action potentially is not the same that create the behavior. We want to expose this behavior to somebody that is less technical, maybe doesn't even know C++, and that maybe wants to change the behavior you did and in some way with different parameters or adding some concept. So we need to think about different stakeholders here. So there is this separation of concerns and separation of users more than concerns that we are trying to achieve. And also we want to express with a domain-specific language this highest level of abstraction in our robot. And there's something very interesting happening here. The very fact that you are using, to be fair, either state machines or behavior trees is that obliges you to encapsulate your code in a more modular way. So this is funny because when you start using this library, you say, oh, now I need to refactor my code to put it into these blocks, so it's extra work. But the very work of refactoring is where you start having modularity and a better code, because you are obliged to encapsulate better the different tasks of your robot. So the side effect of behavior trees is actually one of its main advantages. And that's it. So I guess at this point you can read this, so I don't need to spell it out to you.
Hey, Davide, thanks for your talk. I just had one of the questions about the pre and post conditions. Mm-hmm. So do each one of those create their own node, or is that something in the state machine?
Each instance of the node has those function pointers. So under the hood, there are really function pointers that will execute the scripting language if they are defined, but they are in that instance of the node.
Another quick one, if I may. Does the tick go all the way back up to the main every time and then go down? Or is it passed from leaf to leaf?
So Originally, so usually when you are in a running state, the number of tick is equal to the depth of the tree. So if you are at the level 5, you have 5 ticks to reach you. But of course, if you have a reactive behavior, you want to tick more. So depends. The number of nodes that you tick usually is proportional to the depth, but it can be more if you intentionally use a reactive sequence because you do want to tick more.
Thank you.
Thank you for the talk. I had a question about prioritization. I think that the behavior trees are, because they're ordered, it's representing prioritization sort of implicitly in the order of the tree. So the question is, if I wanted to change the priorities of my robot at runtime, is there a way to do that other than loading a new tree that is a new version of the same tree with reordered nodes?
So that would be a fallback. Create your own control node. So that is the trick, really. So as I said, if you have a special need, and that sounds to me like a special need, you create your own. And actually, I have, people that wants to do something similar to what you just described. And my suggestion is I can help you creating your own priority node that use maybe a variable to decide what is the next most important tick to where to dispatch the next. So in the library, by default, I don't have it, but I encourage people to create their own control node to express the logic they miss in the library.
So in theory, this node could accept some user-specified value at runtime. All right, got it.
Absolutely.
One other quick question. Your Blackboard has shared data between nodes. Does that data go stale, or is the Blackboard reset or cleared in any way?
So the Blackboard usually doesn't clean up itself. So the values you write there are persistent. So if you want to change that, it's your implementation detail. If you want to, reset a particular value, but the Blackboard itself won't reset.
You could, in theory, maybe put a reactive node at the top of your tree that would
that does a cleanup. Yes,
if you wanted to.
Correct.
Got it. Thank you.
Hey, thanks so much for the great talk. Really appreciated it. So I noticed that you went for a concurrent model rather than a parallel model. Obviously, you found some value in parallelism given the parallel control node you specified. How did you decide to go with the concurrent model over a parallel model for this project?
Yeah, mostly for the reason I described, because if I use a parallel model, the ability to interrupt a thread is left to the user. So that is code you write. I have no control if you're writing that code correctly or not. So originally, in the version that I inherited from the original version, each node would create their own thread. I completely removed that because that is a false assumption that when you try to stop the thread, you will succeed. So now in C++20, we have JThreads that can be stopped. But in robotics, you need a cleanup, some kind of cleanups to be done. So you can't expect any magical way for me to halt your thread. So creating my own thread was easy, but created this false sense of security in people. That's okay, so it will magically work. No. So that's the reason why I removed that.
Okay, thank you.
So this idea of suspending tasks that are already running, I'm wondering if that's very similar to coroutines and if you've explored converting this into code routines.
I'm sorry, I didn't understand. Can you rephrase or repeat? Because
so this idea of having a task that you can suspend is very similar to coroutines.
Mm-hmm.
Have you explored converting to use coroutines?
I do use coroutines. So actually there is, that's a good example because here I have a stateful action node. I also have a base action called coro action node. They use coroutines and where you actively yield, you basically call yield. So yeah, I do use coroutines.
Perfect, thank you.
So I've worked on something very similar in the past, XML and everything, but much more primitive. So I really appreciate this. But the behavior nodes, are they thin and they communicate with other real-time control systems, like for example, your shooter or a sprayer or driving.
Yeah.
Those are always present, and these just tell them what to do. Is that how you do
Correct.
it?
In robotics, what we do, as I said before, in robotics, we have these multi-process systems. So the recommended pattern is to just have not your code, but your client to a server in a node and delegate this to another process that does the actual computation. So, but this is very specific for robotics.
If you're driving a path, like a long path, it's not like a path piece per behavior node, right? I'm driving a path behavior, and it does the whole path.
Well, in this case, it could be usually, for example, in the case of navigation of AGV, usually I would implement a go-to, right? To say, I send you the location in the map where I want you to go. So, and that is a classical example of asynchronous action, right? I send you the command, the server will start the operation and update me if anything goes wrong, and then at some point it will send me the signal that the operation is completed. So that is a perfect example of asynchronous behavior. Okay, cool. Thanks everybody.